questo era nuovo. So, okay, last lesson we introduced the state space form. I started with, let's say, the form before even dealing with the models we're going to put in this form. Also because I showed you that also ARIMA models and regression have a state space form. As I told you, the state space form is convenient in many situations, especially for time series. There's slight probability there are also non-time series models in that form, but mostly for time series models. And I already gave you the state space form that we will be using in R, because there's different versions of the state space form. We will be using a patch called FAS. E non funziona neanche. Proviamoci, no? Vuole che appoggio. Allora, intanto c'è sti problemi. Dobbiamo avviare. Ricordatemelo. E tanto non mi sta funzionando. C'è OneNote che... Questo succede a volte quando Windows, senza dirvelo, aggiorna. So basically, we will be using this form for the state space form. Okay, so this is what we saw on Friday. So this is the measurement equation. The input. Okay, that's it. So measurement equation, state or transition equations. Actually, there are many equations. And like the initial condition for the state vector. So alpha is called the state vector. As I told you, usually we have some unobservable components in the state vector alpha. And we have observable time series. As I mentioned last time, y can be scalar, but can also be a vector of time series, so many of them. So this is a vector, this is a vector, this is a vector, 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 vector. All the other ones are matrices. And this is a vector. So we have like unobserved components, and zeta is the matrix that like usually it selects the components, and by summing them all together we get the original time series. This is something called the signal, and this is in some way the noise. So both epsilon and eta are white noise processes, vector white noise processes. And as I told you last time, R is also a matrix which is generally made of 1 and zeros, and it's there just to select the white noise components of eta and give it to the right equations, okay? Because some of these equations are not stochastic, some are identities. So when you have identities, you don't want the noise there. And some of them are instead like processes, so stochastic processes, so we need a noise, okay? And on Friday, we saw how we can cast like a standard regression model in state space form. We saw how we can cast ARMA or ARIMA, even ARIMA models in state space form. Actually, we saw more than one version of that, and I showed you that you can kind of explore by using the Shiny app that I built. It's called SS Maker. Why is this form useful? I mean, we already saw the ARIMA models, you already know regression, linear regression. Why should we use this form instead of other forms? Well, there are many good reasons. The main good reason is the so-called Kalman filter. And also the smoother, which was not designed by Kalman. The smoother came much more later in time. But what are these objects? Well, let's just define maybe some notation. We will call A, maybe T given S, the linear projection, so the linear prediction, whatever you want to call it, of alpha at time t, predicted using all the y's, so all the observable time series, from time 1 to time s. Okay? So I'm predicting alpha, which I don't know. It's unobservable, using what I observed. So y1, y2, up to ys. It's important to see that we gave different name to t and s because according to the relationship between t and s, this object changes name and function. Also, its function is different. And of course, this is a prediction, so we can also compute the mean square error of prediction. Actually, the whole covariance matrix of the prediction errors, which we can call PT given S, which is going to be the expectation of alpha t, the real alpha t, minus its prediction times itself transposed. Okay, so this is prediction of the state vector based on my observations up to time s. So it's the prediction of the state vector at time t based on all observations up to time s. And this is just the matrix of covariances of the errors, prediction errors, okay? So what's the filter, what's the smoother, what's also a forecast? Well, it depends on the relationship, as I told you, between T and S. If T is larger than S, then we have forecast. Because we're predicting the future of the state vector based on past information, okay? If t is equal s, then we have the so-called filter. Filter in strict sense. I mean, filter is a function, it is a name that is used for many things. And the common filter, in strictly speaking, is this object when t is equal to s. So it's like a real-time inference on the state of the state vector alpha t when we have observed everything up to time t, okay? So this is like real-time inference on the state vector. And finally, if t is smaller than s, well, this is called the smoother. And generally, the smoother you compute it using all the data. So s is usually is equal to n when n, meaning that n is all the observations, okay? So the smoother is providing you the best prediction of the state vector at time t, given all the data that you have, also the future ones, okay? So it's not real time, but it's more accurate because it uses all the information available, okay? So forecast, filter, and smoother. This is called smoother because normally it's smoother than the filter. Of course, it's smoother because it uses more information, so the variance of the mean square error are smaller, because if I use more information, the mean square error can only be either equal or smaller. Okay, it's usually smaller. So what you extract, so the time series you extract using the smoother is usually somewhat smoother. And even more importantly than that, it doesn't tend to delay things, because you may so visualize, if I take like, if now by calling a linear filter like a linear combination of data, which is usually, if I can take a linear combination of past and future data in kind of a symmetric way, I'm extracting the signal with the right timing. Instead, if I can only base my inference on present and past information, probably I tend to delay a little bit what's going on, especially if there is noise. So we will see those things in applications later. Okay. And what's the common filter at the end of the day? It's just an algorithm to compute. Well, the common filter actually computes a couple of things. It's like a recursive algorithm that computes. It's got two steps. I will not give you all the formulas, because anyway, it doesn't have any sense that you memorize them. You can look at my book, and they're relatively simple to derive. So it's just, you just follow. In my book, I also consider the case in which the white noise epsilon and eta are possibly correlated, okay? So that makes the common filter slightly more complicated than the one, for example, that we find in all R packages, also in the Python package, okay? So I just define it as slightly more general common filter. But if you put the covariance between epsilon and eta of the common filter, is really simple to derive. But anyway, it's made of two steps, which sometimes for computational speed is synthesized in just one step. But one is called the, I mean, it doesn't really matter from which one we start. We can start with the so-called update step. So the update step takes the previous value of like one step ahead prediction of the Kalman filter. So this is the input, okay, and it outputs. So this is the one step ahead prediction, and it outputs the filter, okay. It's called update because it's like we produce one step ahead prediction of the state vector based on information up to yesterday. Then we observe a new observation today, and we update the inference about the state vector, okay? And the prediction step instead is the opposite. We take the filter and we produce new predictions. Okay. So this is the prediction step. So one step ahead prediction. This is, and of course it jumps up and down. Remember that we provided initial condition for the state space form. So actually, what we called so our initial condition we can see this way, okay. So I gave you these two names, A1 and P1, for the initial condition. We can see those conditions as predicting the first, the state vector at time t equal 1, knowing nothing. So having observed nothing, okay? So you can interpret the initial condition as the first one step ahead prediction in some way. Based on nothing, based on no information. So actually, we initialized the recursion using our initial values, and then you can compute this, of course, and then you go to this, and then you go back to this, and so on. Usually, for computational reasons, you just synthesize both steps into just the prediction step. So you go from one prediction to the next prediction, okay? But if you need also the filter, then it's better you compute both steps, okay? And nice thing about these algorithms is that you have also some, let's call them byproducts, which allow us to compute also the likelihood if you assume Gaussianity of epsilon and eta and so of the data. So, but just to let you understand, so as byproduct, so the prediction step produces also one step ahead prediction of the time series, which we can call this way, which is this is very simple because the system is linear, so the one step ahead prediction of the time series is just zeta applied to the one step ahead prediction of the alpha. Okay. So when we get this, then we can also predict the time series just by applying the matrix. And so we have like the one step ahead prediction. And we also can compute sometimes we can call it E like innovation. The innovation is just the difference between well, I can use t plus 1, and it doesn't really matter. The difference between the real observation and our one step ahead prediction. This, of course, we can compute when we get the new observation, and this is called innovation. In time series, the innovation is the part of the process that we cannot predict. So the difference between the real observation and the prediction. And we are also able to compute the, usually it's called F. It's the prediction covariance matrix. So well, I use another timing. It doesn't really matter. The time is exchangeable. Okay. Or, which is the same, using what we just defined, it's the innovation time, the innovation transpose. And if you want t plus 1, it's t plus 1. I mean, I've been defining everything for t plus 1, so maybe it's better I use t plus 1. Okay, so why is this important? As I told you, this is because if we assume that a reasonable distribution for these two white noise or vector of white noises is Gaussian, and also the initial condition, so alpha 1 is Gaussian, then all, because of the linearity, the closeness to linearity of the Gaussian distribution, then also the time series yt is going to be Gaussian, okay? And we can build the so-called likelihood function. And how can we build the likelihood function? Which is the thing we can use then to estimate the unknown parameters that we do have in a state space form. For example, on Friday, we saw we could cast the ARIMA models in state space form. But the ARIMA models depend on some parameters. We call them phi and theta, and also sigma square, that we don't know, okay? And if we don't know them, how can we cast them in state space form? Okay, we can exploit what I'm going to show you now to build the likelihood function for any vector of parameters. And then, of course, we can maximize numerically the likelihood function in order to get maximum likelihood estimates, okay? So what I was saying is that if we assume that epsilon t, eta t, and also the initial condition, they're all Gaussian, so they're all normally distributed. Well, this implies that yt is Gaussian. Okay, see it here as well. Then one more thing. Actually, the Kalman filter and smoother, they're not only linear prediction, they're also optimal prediction. So this implies, okay, yt is Gaussian, but this implies that this is also equal to the expectation of alpha t given the information up to time s. So I defined to you alpha as the linear prediction, but if you recall our, I would say, second lesson, I showed you that in case of Gaussianity, linear prediction and optimal prediction are the same thing, okay? So the conditional expectation, which is the optimal predictor in case of a square loss function, in case of Gaussianity, is also linear prediction. I mean, the linear function is optimal if you have Gaussianity, okay? So actually, if I assume Gaussianity, then the common filter and the smoother, they do not only provide linear prediction, they also provide best prediction possible. So the conditional expectation, okay? And of course, we also have that, but this doesn't change. This is also, I would say, the conditional variance. Okay. Okay, so how can we write the likelihood function? Okay, in IID statistics, so when you have IID samples, so Bernoullian samples, if you remember from your basic course of statistics, when we observe, I don't know, n observations, and we have a density, for example, the Gaussian density, we're and of course, this depends also on some parameters that we want to estimate. Let's call them like theta. Well, we can redefine this object as the likelihood function just by saying, okay, we see this object as a function of theta given all the data, okay? And more importantly, we can factorize, maybe I just do the factorization before the definition. But usually we can factorize this by the product of all the marginal densities. IID, what does IID mean? It means independent, identical distributed. So every observation has the same density. So each one of them has F as a density. But more importantly, they're independent. So the joint distribution is just the product of the marginal distribution, right? So this is the word of Bernoullian samples or IID samples or whatever you want. Of course, this does not hold in time series because we don't have IID samples. Let's call them samples. Actually, we are very happy if the samples are not IID. Otherwise, we could not predict them. If our data were IID, the best prediction I can produce is just the average, the mean of the data. Okay. So we are happy that the y's are not independent, but then we have to change our factorization. So in time series, we can factorize density, the joint density, as product of the conditional densities. So it would be the product for t that goes from 1 to n of the density of the t observations given the past. Of course, when t is equal to 1, this is going to be empty, okay? It's going to be just the density of the first observation, okay? Okay, let's go one step further. We're assuming in our model that, and of course, this depends on a set of parameters. I didn't guide it. Well, I wrote it there. This also depends, of course, on a set of parameters. Let's go a step further. I told you, if we assume Gaussianity of all those epsilon and initial condition, then also the data will be Gaussian. So this is just a conditional Gaussian. The Gaussianity is also close to conditioning, so this is going to be, again, a Gaussian. So this is going just to be a product of Gaussian densities. I don't know, I can call them, well, we could even write them down, but anyway, it will be, let's call it, usually the Gaussian density is called phi. Given the mean and the variance. But what's the mean and what's the variance? Actually, it's a multivariate, so we have a vector of mean and a covariance matrix. Okay. So these are going to be Gaussian. So what's the mean of yt given the path up to sine t minus 1? Well, it's the one step ahead prediction of yt. So this is just yt given t minus 1 half. And this is its variance, which is just, we just named ft. Okay. So as you can see, we can write the joint likelihood of all the data just as the product of the Gaussian density computed at each observation yt, where the mean is the one step ahead prediction, and the variance is the variance, the one step ahead prediction, which we saw that the Kalman filter is providing us with. Okay, so the Kalman filter computes this as well and this as well, and so we have everything we need to compute the joint likelihood of the data. Okay, as you probably know, usually we don't maximize the likelihood, but the log of the likelihood. There are good reasons. There are good both computational and theoretical reasons for doing that. Well, the first problem is that this is a product of numbers that can be very close to zero. Okay, they are probabilities, okay, density, probability density. So if I multiply many time series that are close to zero, probably I have problem with the precision of in a computer, okay? If we take the log, then we have sums, and sums are kind of more stable. And I can stabilize them even better by maybe taking the sum divided by n, so the mean instead of the sum. But so these are the numerical reasons why usually it's better to work with the log likelihood. It's simpler to maximize the log likelihood. So usually we work, as I told you, this weekend, usually we call L theta given the data. So we want to see the density as a function of the set of parameters that I have to estimate. This means that I can try to set values for this vector of parameters, and I will get a value of the likelihood. Of course, my aim is to find the set of values in theta that maximizes the likelihood. The interpretation, of course, is I'm trying to find the set of unknown parameters that make the observed data that I have obtained the most likely to observe. Okay, it's like an optimistic way of seeing things. So maximum likelihood means just find the parameters in such a way that my data that I have observed are the most likely to observe under the model. This is one way to see the maximum likely estimation. There are also other ways. But anyway, I told you, usually we work using the log. Usually we use the small l for the log likelihood. And of course, all of what we have seen, everything becomes like the sum of the log of normals, well, with mean T equal T minus 1 and variance covariance matrix. Okay. And this, of course, we can compute, and this is, and this, of course, depends. So both the mean and the variance depend on the unknown parameters. Okay. So I enhance this here. Okay. So according to the parameters that I put into the system, I will get different predictions. And according to this different prediction, I get different values of the log likelihood. And we want to maximize. So our maximum likelihood estimates are, which this is a vector, okay, are the R max of so these are the maximum likelihood estimates. Okay. So you can see like two levels of inference in modern state space form. One part of the inference about the state vector alpha t, is carried out by the common filter on the smoother. But the inference on the parameters that we don't know inside the state space form, usually there are variances. Sometimes there are also some coefficients that we have to estimate. The variances on those parameters instead usually we carry out by maximal likelihood estimation. There are also other ways you can also attack the problem with Bayesian statistics, but here we just cover maximal likelihood estimation. Okay. So the Kalman filter gives us not only at the end of the day the inference on the state vector, but it gives us also the possibility to build the likelihood function given a set of parameters theta that we can then maximize numerically using the optim, for example, R, to find the best set of parameters. The best meaning that it makes my data the most likely to be extracted under the model that I'm using. Okay. And as I told you, this is just one way to see maximum likelihood. You can also see as the method that minimizes the discrepancy between your model and the real model, which you don't know, using as this discrepancy the Kullback-Leibler difference. Kullback-Leibler criterion. You can see it that way as well. But this is more intuitive. This is how it's actually was born in the 20s of this century. Okay, maximum likelihood. We also actually know the properties of maximum likelihood, or at least the asymptotic properties about maximum likelihood estimate. In this, let's say, more data science-based course, I will not give you too much information about maximum likelihood theory or asymptotic theory or maximum likelihood. But anyway, I can tell you we are able to derive the uncertainty about the estimates of the parameters. If you ever, probably you've seen this result in the past. Do you know what the information matrix is? So the information matrix is just minus the second derivative of the log likelihood, so the of L, with respect to the parameters. Of course, sorry, the expectation is missing. the expectation of the second derivative. Okay, why the expectation? Because this is a random variable. Okay, so we can compute the expectation because this is a random variable. And the asymptotic theory is telling us that if I multiply by the square root of the sample size, the difference between my estimates, which is what I can enhance the factor is based on n observations, minus the real set of parameters that we can call theta 0, then as n increases, this converges in distribution to a normal with zero mean, well, zero mean, not theta, vector. And the variance covariance matrix, which is given by the information matrix computed at the maximum, at the real value. So this is the asymptotic theory. The asymptotic theory tells us that, okay, if we have a large enough sample, we can estimate for example, the standard error of this estimate based on this matrix. Of course, this matrix is unknown because it depends on the real parameters, theta 0, which we don't know. We want to estimate that. But then what we can do, we can estimate this variance. So let's see, we can estimate the information matrix at the real parameters value by taking the average of the second derivative of the contribution of the to the likelihood of the t observations. Okay. And of course, we can compute this at the maximum likelihood estimation. So this derivative is computed for theta at the maximum likelihood estimation. Okay. So usually we can estimate the standard error of the estimates by just computing this object here, which is actually very simple to compute because of the linearity of the derivative. We can switch between the derivative and the sum. So this will be like the second derivative of, and here we get the log likelihood. So if I sum all this contribution to the log likelihood, I get just the log likelihood of all data. So that we are able to, actually we just compute it, okay? And this is very simple to compute numerically because we have a function to compute this. No, we have like an informatic function to compute the likelihood given theta. And the second derivative, we can ask any computer to come to approximate the second derivative using the Hessian. So the Hessian we can compute using small differences. Okay. So for example, in R, if you ask optim, if you want also the Hessian, you just set the Hessian parameter equal to true, and we'll return also the Hessian at the maximum. But anyway, even if you don't have optim, you have any other optimization tool, you still have usually like a way to compute the numerical Hessian. So actually, this is very simple to compute. So this is maximum, the likelihood, you compute the second derivative of this at the maximum. If you cannot do it analytically, you can do it numerically. So actually, it's very simple. And we have an estimate of the, for example, the standard error of the parameters. So you can test if they are 0 or not. You can test if they are equal. We will not be using that too much in our models, but you can do. We could do it as an example, actually. Usually we just are happy with the point estimates. But of course, if I want to build inference on the estimated parameters, I need this result from maximal likelihood. Okay. Good. So we have a form. We know how to compute inference on data in this form or time series models in this form. Now we need the models. I mean, we have some models, but we could try also, just for example, also to take a regression and put it in state space form, or an ARIMA model and try to estimate it in state space form. But the state space form is particularly useful for the class of models that I'm going to talk to you about, which is the unobserved component models, which are naturally in state space form. One more thing. I told you we always have to deal also with initial conditions. Which are, yeah, this object here, okay? So the state space form needs initial condition, okay? I gave you already some ideas on how we could compute initial conditions. So basically, if you have some of the state vectors that are not stationary, then you have two possibilities. You can either set the variance to infinite. Setting the variance relative to that state vector to infinite means I know nothing about the value of that alpha at times t equal to 1, okay? So you can express your total ignorance about the value of every single state variable by setting the variance equal to infinite and setting the mean equal to whatever you want. Because if you set the variance equal to infinite, it doesn't really matter what's the mean that you fixed, because it means I'm completely ignorant. As far as I know, that number could be between minus infinite to infinite, because I know really nothing, okay? Instead, you may know something also just from reasoning. You may say, okay, this is, for example, the component that represents the trend or the level of the GDP at times t equal to 1. Well, probably you have some idea of what number it could be. I don't know, this is the Italian GDP, I don't know, maybe it was year 2000. Okay, the GDP of 2000 cannot be that different from today. Today, the GDP of Italy, I don't know, it's 2000 billion or something like that. So you have kind of the unit of measurement of your variable, and you can try to turn that into its Gaussian. And we're assuming our knowledge about that value like a Gaussian distribution. I can put the mean to what I suspect to be a decent value, a decent estimate, and put the variance of that or the standard deviation of that Gaussian, so that it includes at 99% all the interval, I think, of reasonable numbers. For example, we will do example about that, okay? But I can fix sometime by using my knowledge, my previous knowledge, the initial condition to a better value than just the infinite variance value. Instead, if we have a stationary component, for example, we will see that, well, some components, as I mentioned on Friday, could be also ARMA, stationary ARMA models. For stationary ARMA models, we can always use the marginal mean and the marginal variance of the model as initial condition. That's actually the correct way to manage that. We'll return to that, but I'm just giving you some setup, and probably it's already too many information, too many pieces of information. But then will apply them and probably will understand better what I mean. Let's start, even before starting with the so-called unobserved component models. Let's start reasoning on a real problem that I was asked last year to model, which I think is a good way to see how this form can solve problems, real problems, even without knowing anything about unobserved component models. So, for example, it was last year that we had to vote for the European election. And this firm came to me and said, I would like to make a daily indicator or a daily estimate of the number of votes, of the percentage of votes for every party based on, and they had 40 institutions that were doing surveys, so political polls. And they had this time series starting from 2018 with the polls for all the major parties in Italy. Of course, polls are not every day, and not all companies do the polls on the same days. But what I didn't tell you is also that the nice thing about this setup, so the state space form and common filter, is that missing observations are not an issue. You can have missing observation wherever you want. You can have the whole vector missing on some days or some time t. You can also have some parts of the y vector missing. The common filter, and so the likelihood maximization work even if you have missing observation. The common filter has a slightly different step when you have a missing observation, but we know how to compute that. And it's still computing these quantities that I mentioned. Okay, so it's always doing, even if some, for example, if observation number 2 is missing, okay, it's just computing the same prediction based on the fact that observation 2 is missing. Okay? And so actually we are able also to produce optimal imputation for missing observation. So I didn't tell you that, I'm telling you that now. So let's start with the basic problem. So we have for so we have, well, the problem, we can call it either pole or poles. Something it's called this way. It's like un sondaggio dei sondaggi, pole or poles. So we have many, like a vector. Suppose, let's just take one party. So for each party, for party I, okay, actually we use I, so J, we have a vector of percentage. It doesn't really matter that it's a percentage, but it's vector with 40, this is a 40 times 1 vector that at time t is telling you how many, or what's the percentage of votes estimated by the first company, the second company. There's 40 companies. Some of the company will be missing, some not. It doesn't really matter, okay? So this is a vector with, I don't know, so this is, our y is the votes at time t estimated by company 1, by company 2, up to company 40, okay? So we have like 40 measurements of what? of one single value, because everybody is measuring the same thing. Everybody is measuring the right percentage of votes in the population, okay, or intention of voting. Because of course, until you have not voted, you don't know the real number. So this is just like the object of these surveys or these polls is measuring the intention of the population for voting for that party, okay? And we have up to 40 estimates of that, but everybody is estimating exactly the same number. So the real value of the votes or the real percentage of votes that in that moment is, if we could like ask everybody, would come out of the population, okay? And we can call that real number of votes mu, okay? So this is the real unknown, real percentage. Intention of voting for party J, okay? And these are like the polls, 40 polls. So you can think that every single number here is a noisy measurement of this field, right? So we may say, okay, everybody is trying to measure that. So every number is equal to the real number, which we don't know, plus some noise. Okay, that's reasonable, okay? So there's a real number of or percentage of votes we don't know. Everybody is trying to measure that, but everybody is committing some mistakes, which is this noisy part, okay? And of course, the mistake variance will depend on what? Well, on the sample size, for example. Every single company here is asking a different number of people what they're going to vote. So we may assume that the variance here of each of these errors depends on the sample size, of course, inversely. So it's we know that, for example, if I estimate the mean, estimated percentage is just like estimating the mean of a 1-0 variable. So you ask people, are you going to vote for party J? They're going to answer yes, no, 0, 1, or 1, 0, yes, yes. And so the percentage is just the mean of the one of this 1-0 variable. Okay. So the estimation of a percentage is just an estimation of a mean. Okay. We know that the variance of the mean is proportional to 1 over n, where n is the number of observations. Okay. So we can expect that these variances are proportional to 1 over the number of people that were interviewed. Okay. And then actually it could be even proportional to the company being good or not good in doing their job. That's of course. So we can assume either like a common variance divided by the sample size. In that case, we are assuming all companies are good as any other company in doing that job. So their precision in estimating the real mu depends only on the sample size. This could be a good assumption. In that case, we could assume that the variance covariance matrix of all these errors, well, of course, we assume Gaussianity, the mean of the errors we assume to be 0. And the variance covariance, as I told you, we could just suppose it's just like a common variance divided by the number of interviews for company 1, for company 2, and so on, and so on. And then we can just assume that there is no correlation between the errors. I mean, unless the companies call each other by telephone and that influencing the published number, otherwise there is no reason why there should be a correlation between the error that his company and my companies are making. Okay. So we can assume, for example, that the variance covariance matrix of epsilon is just diagonal. This is the precision of the estimate, and it depends only inversely on the sample size of the interviewed people, right? Are you following? Is everything clear? So this looks like an observation equation, right? So this is like the observation we had. This is the matrix zeta. This is one just state variable. We just have, in this case, we just have one state variable because there's just one number we want to estimate in this case. But this number is observed with noise, and we know we built this noise, and we also kind of built a rule to give variance and covariances to these noises. What's missing is the evolution of the number. Of course, every day people can change the idea, and so we can assume that mu t is not constant over time, but is evolving. And so you can propose some idea on how can we let mu evolve over time. So this would be our state or transition equation. So how we can suppose that this percentage of votes is changing from one day to the next one? Well, we can just say, okay, maybe the votes of tomorrow are going to be like the votes of today, plus some random noise, right? So like a random walk at the end of the day. So this is the percentage of votes of tomorrow is going to be equal to the percentage of votes of today plus some noise. This is reasonable. Okay. We could even add some trends. I mean, this is a trend, but it's a completely stochastic trend. If we think there is like an increasing trend for the parts, and so we could even change this to include that. And we will see in our unobserved component models how we can do this. But this is very reasonable. Well, my dear, we just built a state space form for this problem. And the nice thing is that, as I told you, this vector will be a very sparse vector. Sparse meaning not because we will have many zeros. Now, that's probably sparse is not the right word for this. It will be a vector with many missing observations. On some days, all observation will be missing. If on some day there is no pole, then this vector will be a vector of missing numbers. But as I told you, one very great thing about state space form and common filter is that missing observations we can deal with. It's not a real problem. Okay, so we just found a solution. And what about the? We're interested in producing like a daily estimate of mu t, and this is what the common filter is going to produce, because the common filter is giving you, under Gaussianity is giving you the expectation of mu given all the past and present observations. So the common filter is just providing you with a real-time estimate of the mu t. The smoother instead will give you like an estimate based on all observation of the present value of mu and also of the past value of mu. So it's more of an analysis, like historical analysis, what we can do. Of course, the smoother and the filter, when we are at the very last observation, they're just the same number. Okay. But of course, it changes in the past. So the smoother also changes the past. Indeed, I didn't show you how the smoother works. The smoother works backwards. So first you pass the common filter starting from observation number 1 to observation number n, and then the smoother works backward from using the common filter and the data from the last observation toward the first observation. So it's like correcting what the common filter produced by taking into account the fact that we observe data after the common filter. So it's like a backward correction of the common filter. And so if we have to do a historical analysis on the votes that we, or the percentage of vote that we observed in time, then the smoother is the right thing. If we were just interested in estimating in real time, what's the best estimate I can do for today of the number of percentage of votes for this project, and the common filter is the right tool, okay? And of course, I can do also prediction. I mean, within the framework of common filter, we have also formulas for doing the prediction. So everything is coherent and everything is contained in the state space form in all these algorithms, okay? Actually, we could even try to apply this because I have the data of this free example. But we don't know yet how to work with the state space form in FAS, which is the package we are going to use. In R, there are at least 4 or 5 packages to do like state space modeling and in common filter. One is even in the standard stats library. As I told you, if you select maximum likelihood for the ARIMA models, then what R does is set the model in state space form and then use maximum likelihood based on the state space form. So that's why there's already present a common filter in the basic R distribution, but there are packages that offer more. For example, the common filter within R is only able to work with one Y, so it's only univariate and has other limitations. So it's we will not be using that. But there are many packages. I would say the best one are 2. One is the one we are going to use. And there's also this one. So this is the one we're going to use. There's also this fast common filter. So this is just fast common filter. But they're both computationally very well made. This is based on Fortran code. This is based on C code. But of course, we just use them using R. This has many more functions to work, and also makes state in typical modeling state space form very simple. So this is a good compromise between flexibility and easy of use. This has just 2 functions, I think. One to compute the filter and the other one to compute the smoother. So it's very basic. This is also fast. Anyway. So we will be using this. So let's just, I want just to start telling you how to set model in state space form, so we can start both by analyzing the unobserved component models, but setting them right away in state space form in R. And of course, there's the time series library in Python that has also the state space form and common filters. Actually, also in Python, you even have more ready-to-use unobserved component models. They're a little bit less, they cut a little part of the work, but we'll be using R anyway. So, as I told you, we're already using the symbols of on the form of class. So you will find in class the zeta matrix, okay, the H matrix, which is the covariance matrix of epsilon, that could possibly be time varying, and also Q, which is the variance covariance matrix of the eta. So the matrices that you will find in class are, for the observation equation zeta and H, they could be static or they could be time varying. Keep in mind that inside a class, they will be always, they always will be three-dimensional arrays. Even if they don't change in time, internally, zeta and H, but also the other, will be three-dimensional arrays. So if they change in time, the third dimension of the array will be the time. If they're not changing in time, then the array is really useless because there's just one time value, okay? And of course, there will be matrices. Then for the state vector or state equation, we have the T matrix, again, would be an array of either n third dimensions or just one element in the third dimension. R, same thing, and so the Q. And then, of course, there is the A1 and P1. And actually, in class, we have A1, P1, and also P1 inf. So, what's P1 inf? We will have P1 and P1 inf. How we can interpret it? We can interpret it this way. So the variance covariance matrix of the starting value is made of P1 plus, let's call it K, times plus 1 inf, with K goes to infinity. So actually, the only thing that counts in P1 inf is the diagonal, okay? If you have 0, all the rest is always 0. So we have only a diagonal matrix. We have 1 on the diagonal if that element receives an infinite initial variance, and we have 0 if that element receives a finite variance, okay? So the only important thing here is the diagonal. It can be 0 or 1. 0 indicates that that variable has a finite variance. 1 indicates that that variable has an infinite variance. So that's why you can see it this way. And here, if here there is a 0, then that variable variance is taken from here, and also the covariance with the other variables. Instead, if the diagonal of that element is infinite here, well, this part is ignored because the infinite prevails on the finite. So it's just because there is a different Kalman filter. If you have, it's called the diffuse Kalman filter. Okay, when you have infinite variances, we call this also diffuse condition. A diffuse distribution is the distribution with an infinite variance. Okay. So you have to indicate which variables receive an infinite variance, because the Kalman filter for those variables will be slightly different than from the other variables. Okay. So this is the only thing that here is in class which we didn't define into the model. It's just a way to symbolize a matrix with a part which is finite, a part which is infinite. Okay. And the nice thing about the basic constructor. So what's a constructor? A constructor is a function that produces an object. Okay. So the basic constructor in class that produces an object of SS model class is called SS model. And it takes the formula here. The formula is particular because we could have regressors here as usually. Well, you can say 0 if you don't want, for example, the intercept. You can also have the regressors, and then there will be some components. I could have SSM, for example, also ARIMA. If I want to add an ARIMA model, and this is a function, of course, that takes the parameters of the ARIMA, I can have SSM trend, for example, if I want a stochastic trend. We will see in theory first and then in application how to use that. We can have one or more seasonality. Okay. Or I can also use SSM custom if I want to define a whole state space form as I want it, or just part of the state space form, which is not already included in one of these like utility functions. So what this thing here does, it builds the state space form. If you have typical models, you don't have to write it yourself, the state space form, because this function produces by using this information. If instead you want to define the state space form completely customly, you can use SM custom, but you can also use a mix of these things. You can say, okay, the components that I need is a trend, which is already inside this package. And the other component I want to use is not present in the package, so I have to define only that component using the SSM custom. So it's just part of the model or part of the state space form, okay? And everything is usually closed by the definition of H. And of course, I can use, I don't have to use data if I want to take the variables from a data frame, okay? Oops. And this is just to build the form. And then we have to estimate, I mean, if all the variances, all the other parameters are known, this is already a usable state space model. Then I can pass it to the Kalman filter, to the smoother, to make prediction, forecast, whatever. But usually, as I told you, some parameters will be missing. For example, let's go back to our example here. What are the parameters that we don't know here? Well, we don't know, say, the common variance here of the sigma square is to estimate, and also the variance of the eta. So eta is the shock that lets the percentage of vote evolve over time. Of course, the larger the variance, the quicker the people to change their mind, and the closer to zero of the variance, the more stable the people intention of votes will be. Okay. So in this case, we have two variances to estimate. Okay. So we will see that the variances will be defined wherever in the component, either here or here. We can also put arbitrary number because anyway, we have to estimate those numbers. And there's another function to estimate the unknowns is the fit SSM. And fit SSM needs initial values, and that's the sad part. So initial values for what? For the unknown, for example, for the two variances. Because fit SSM actually has optim inside. It's just a numerical optimizer. A numerical optimizer always needs starting values because it starts from the starting values that you provide and then tries to go up. Actually, this tries to go down, so it takes minus the log likelihood, but it doesn't really change, okay? So initial values are the, let's say, the part that takes sounds a little bit more of a reasoning, but it's not that difficult. They could be also rather arbitrary because they're just starting points. But then it takes, first it takes the model and then the initial value. So first it takes an object of SSS model class, so a state space form. It takes initial value, I think it's called init, and then it takes a function, I think it's called update fn, and this is important. This function so we have like a vector, here is a vector of initial values, and this is an update function. The role of the update function is it takes the model, the state space model, also here it's called just model, and it takes the parameters, which calls parse. What does it do? So this is the vector of parameters. It takes the parameters, put them in the right matrices, whatever they have to go of the model, and return the model, the updated model. Okay. So first of all, we have to create the state space form. The state space form, we have parameters that we have to estimate. In order to estimate those parameters, we have to use the fit SSM function, which uses a so-called update function that takes the model, the state space form, and the parameters. And what you have to define here is where each of the parameters that you want to estimate has to go inside the state space matrix form matrix, okay? So some parameters go into Q. Often we will have just variances. For example, in the example that we just made about the polar poles, we just have two variances to estimate. One goes into the Q and the other one goes into the H. Okay, so of course H is here. Okay, but in this case we just have two variances. We have to set one variance here with the other one is here. Okay, and then of course return the updated model. What fit SSM does is start from the initial, so the init values, and then using the optimizer, the R optimizer, which is called optim, it tries to maximize the likelihood by changing the values of theta. But of course, it has to know where to put the parameters inside the model. And that's why you have to define this update function. There is a default function, and the default function assumes that you just have to estimate variances, so only variances, which are on the diagonal of Q and on the diagonal of H. Okay. So if you only have, like in our case, variances to estimate, you can just set them to NA, so missing value, and the default update function will assume that if it finds an NA on the diagonal of Q, on any diagonal element of Q and also of H, those are the variances that have to be estimated. So this is basically how fast reasons. I mean, it's at the beginning maybe will be a little bit of work to remember all those things, but I see that students at the end of the course and during the examination. I mean, examination is different here. There is no live use of this, but anyway, at the end of the course, usually you're pretty familiar with this. Of course, if you use Python, you can use the tools there, which are in some way simpler to use, but not as flexible as here. And I think that you have not noticed, also we can include the regressors, and it will be the SSM model function that automatically will set this into state space form, adding the regression coefficient for every regressor in the state vector. We can start with some simple example now. Well, we don't have much time. For example, just very quick example, and then we can just leave. So that you kind of get also the feeling of how FAST works. Let's just try a simple regression model, because everybody knows the linear regression. So, and we already saw the example of a regression in state space form on Friday. So I'll just create artificial data. So X will be just, I don't know, something that counts from 1 through 100, and Y will be just X plus some random noise, normal noise. Let's put some more variance, like 3. Okay, just a stupid linear trend plus noise model. Okay, let's load the library FAST. If you don't have it, you have to download it. As I told you, the first thing we have to do is defining the model. Of course, you can look at the help. The help, you have SSS model together with all the utility functions to build the state space form for some particularly interesting form of models. For example, the ARIMA are there. This is custom, so this you make whatever you want here. This is for the cycle. We will see that in the unobserved component model. Well, this is also another regression, but actually we will be working in a simpler way to produce the regression. Seasonal component, different seasonal components, the trend. So you see there's already many utility functions, but let's just start with a very, very simple model. I need the formula, which I cannot reproduce here because I don't have the tilde. So I steal the tilde from here. So if I just want to compute a regression, and maybe let's just set the variance equal to the real variance for the moment. And we will have to estimate this, okay? But at the moment, just put a model where there is no unknown, okay? Okay, that was the model. How can we look at the model? Well, it's simple. Just you can extract all the matrices. They have just the same name as I used. So, well, this is the time series. This is the zeta matrix, H matrix, the T matrix, and so on. And these are the initial conditions: A1, P1, P1E. All the rest, it's not interesting to you. So let's go back to yesterday. So the regression. Regression example. Where was it? Here. So in linear regression, if you remember, the zeta matrix is just the matrix containing the regressors. Okay, and the state vector is just a state vector with the regression coefficient, and they have to be constant. So there is no Q variance, okay? So if we look at the T, actually there's also the intercept, because if I don't put the 0, then by default there's also an intercept. So the intercept is just a constant equal to 1, but this is the transition matrix. As I told you, it's a three-dimensional array, but the third dimension is just fixed to 1. And we have just an identity matrix. Why identity? Because it's just telling the intercept of tomorrow is equal to the one of today. The regression coefficient of tomorrow is just equal to the regression coefficient of today. Okay? What about the Q matrix? Well, the Q matrix actually doesn't even exist. Well, actually, they produced that of dimension 1, but with variance 0. And probably there is a, I don't know why they chose, actually you could define a matrix of dimension 0. In this automatic thing, they didn't do that. And the R matrix is just 0, 0. It's just telling there is an arrow with variance 0, so which is always equal to 0, and you multiply that by 0. So there is just 0. As I told you, actually, we could have defined a matrix of dimension 0 times 0. It's strange, but you could. But more importantly, of course, H is just the variance of the noise, because H is the variance of the white noise sum into the signal. And the only interesting thing is this zeta, which is you see, it's an array with 100. So in this case, the third dimension is working. Why is it working? Because we have a regressor, so the zeta is different for every time point. And the first value of the zeta is always 1 because it's the intercept. But the second value of the zeta is the x, which I created. So it's the counting from 1 to 100. Okay. And yeah, and we just stop here because there is no more time. But then we will see how to estimate the unknown of the model. So, for example, if I don't know H, in this case, I just fix it, but I should estimate it. And even more importantly, the regression coefficient that will be just given by the common filter and smoother. And then we will start defining all the rest of the unobserved component models, which is the main point of this part of the course. Questions? See?
So these are not time series.
Oh, you could define it as time series object before. Actually, by default, I think it returns everything in TS, but yeah, you can define. And votate. Fra poco metto tutto quanto, così prendiamo una decisione finale.